Hello, and welcome back to my YouTube channel. My name is Professor Govalla, and today I'm going to be talking to you about clipper circuits. Specifically, we're going to dive into the series clipper circuit and the parallel clipper circuit. And in the series clipper circuit, we're going to be talking about the positive series clipper circuit and the negative series clipper circuit, as well as the positive parallel clipper circuit and the negative parallel clipper circuit. So to begin, this is the negative series clipper circuit, and we call it in series is because the diode shown here and the resistor are in series with one another in comparison to a V out. This is a V out, so this is your V in. And essentially what we know about diodes is that we need to apply a certain current, and there's a drop of 0.7 volts through this diode, and it turns on, and then the current keeps flowing. So for example, if your input looks like this, so if my input imagine if this is 10 volts and this is negative 10 volts. If my input has a positive wave, let's go ahead and draw our output as well. What's going to happen is it's going to require a certain amount of voltage before this output resistor turns on, and it's going to be a voltage drop of 0.7 volts here at the diode. As a result, the voltage drop of the resistor is going to be 9.3 volts to satisfy this VI of 10 volts. When we go towards the negative direction, so like this, the current is going to flow in this direction. And for a diode, this just looks like an open circuit. So this here is an open circuit. So I'll do that in blue. As a result, no current is going to flow, and the negative part is going to be clipped. So again, if I draw another positive wave, it's going to flow through, but the negative is going to be clipped. So this is why it is called a series. Again, because the diode and the resistor are in series and compared to VO. And then it's called a negative clipper because my negative terminal, my negative voltages are being clipped. So I hope that makes sense. Let's go ahead and talk about the positive series clipper circuit. So in this circuit, again, when looking at VO, we see that they're in series. But again, why is it a positive clipper circuit? So if we have our input, as we said before, this is 10 volts. This is our input. And our output, when we input a positive sign or positive waveform, that means the current is going in this direction. This becomes reverse bias or open circuit. As a result, no current flows through it. Okay? And when we have the opposite direction, so when we go in the negative direction, this becomes what we consider forward bias. So there's a plus minus 0.7 drop across of it. So here will be a plus minus 9.3 volts across the resistor. So here we would have 9.3 volts through our output. Let me be, this is 10 volts. This is negative 10 volts. This should be negative 9.3 volts. And again, if we do another waveform, it will be clipped and this will pass through. So I hope this makes sense as time goes on. And again, it's considered a positive clipper. So the positive clipper comes from the positive end being clipped. It's in series, so we call it series. So it's a positive series clipper circuit. Let's do a quick example. Imagine you have your circuit like this. This is this is a circuit R. If I go ahead and input, let's say 10 volts, a square wave, that is 10 volts plus or minus 10 volts. The output here essentially will be, this is what we consider, so it's a series, so it's because in comparison to the output, VO, it's in series. And this is so when I put in current here, it passes through 0.7. So that means that when I go the negative direction, it's going to be open circuit. So that means all my negatives are going to be clipped. So this is a negative series clipper circuit where my output is going to look like this. And maybe pause the video and tell yourself what voltage this will be. Okay, so I hope everyone got the voltage. This voltage here will be 9.3, given that this is a silicon diode with a plus minus 0.7 volt through it. Quick side note, you can have a silicon diode with 0.7 volts through it in forward bias, and a germanium diode, and this gets 0.3 volts through it. And this is used in high frequency application and for signal detection due to lower forward voltage and faster responses. And this one, so that's the germanium. And the silicon diode is commonly used in power electronics and digital circuits due to its high breakdown voltage, and it's a little bit more stable. All right. So now let's dive into the next topic, which is our parallel positive and negative clipper circuit. So in this example, or in this configuration, we have a negative parallel clipper circuit simply because if this is my V out, it is in parallel with this diode. Okay, so let's go ahead and analyze this. So if we put, this is my input, let's say that this is 10 volts and this is negative 10 volts. If we put a positive waveform through it, what's going to happen is it's going to go here. And since this is in reverse bias, we're going to see an open circuit here. So my current isn't going to want to flow through here, but instead it's going to want to flow through here. And in order to find the voltage through this resistor in this configuration, we say that VO is equals to VN RL over RL plus RS, or this is our voltage divider equation. And we can draw our V or our output And we can say that this is a certain V out. So again, our output is going to come here, and it's dependent on this voltage, V out. And then what's going to happen when it goes the other direction? So in the other direction, this is now going to act as a forward bias. So let me use a different color. So in the other direction, this is going to act as a forward bias. And there's going to be a plus minus 0.7 volt drop. And essentially after 0.7, this is going to act as a short wire. So my current isn't going to want to flow through this resistor, but it's going to want to flow through this short circuit and follow the loop. As a result, since this is 0.7 from A to B, this is also going to be 0.7 from this A to this B. So the drop across the resistor drops down to this 0.7 and comes back up. Or let's go with red. So it comes here. And then, so if this was going down here, it gets shunt to 0.7. And then it comes back up like this. And this one comes back up like that. And then again, if this one just goes down, this gets shunt to here. So essentially, this is your negative parallel clipper circuit. Again, in the negative part of the waveform, it gets clipped. And we are in a parallel configuration between the diode and the RL. So it's called a negative parallel clipper circuit. So this is the last configuration. And as you can see, again, if we consider this to be our V out, it's in a parallel configuration with this diode. And again, we can say V out is equals to RL over RL plus RS times V in. And if we wanted to plot this for a given input from 10 to negative 10, so let's say we get a positive wave, another positive wave, a negative wave, and another negative wave. We can see that for our output, let's go ahead and see what happens. For the positive waveform, when we pass this through here, there's a drop of plus or minus 0.7 if this is a silicon diode for it to keep going. And so the drop across this A and B is 0.7. So the drop across my V output A and B is also going to be 0.7. So for a positive part of our waveform, we see that at 0.7, it gets clipped. All right. And then the negative part of our waveform, when we push it this direction, again, it looks into here, and this is in reverse bias. So this is open circuit. So current's not going to want to flow through this high resistance. So it's going to come in this direction through this RL. And this just becomes a simple voltage divider circuit where this is VO or negative VO. So it comes down to negative VO. Again, it gets shunt here at 0.7. And then it comes down here. So I hope this concept of a positive parallel clipper circuit makes sense. Again, we can decipher this. It's a positive clipper because it gets shunt at the positive side of the waveform. and it's in parallel with the diode. So we said that the diode, if we can redraw it, these two are in parallel. So let's do two examples to really get an exercise about these circuits. So this is the first example, and in this example, we're set to consider a germanium diode. So that means that the V threshold across the diode is going to be 0.7 in the forward bias region, 0.7 volts. So we know that this is a negative parallel clipper circuit. So we know that if I have my input is something like this. Oops, man. And this is 5 cosine, so 5 here, -5. This is my input. So we ask, what is the output going to be? And essentially, we know that the negative portion of it is going to be clipped. So it's going to look something like this. Let me do it in blue. All right. And we said that this was this VO, and this was the V threshold. So in this case, it's going to be negative 0.3 volts. But let's analyze the circuit. If we put our positive in through here, we see that this is an open circuit. As a result, current is going to flow through here. The voltage VO is a current divider. So VO is equals to 5 times 5 over 10. These are K's, but they cancel out, which is equals to 25 over 10, or just 2.5 volts. So this VO is going to be equals to 2.5 volts. And in order to find my shunt, 0.3, the way we can see it is that in the negative direction, let me use a different color. In the negative direction, this is forward biased at 0.3. So the difference between A and B here would be the difference between A and B here. As a result, the drop across this resistor is also going to be 0.3. And that's how we get this shunt right here. For the last problem, we have a similar circuit, but now we change the configuration of our diode. So this becomes a positive parallel clipper circuit, right? Again, these two are in parallel, and we're going to see that the positive terminal gets shunt out. So imagine we have an input. Again, it's a 5 cosine, so this looks like this with a VP. Oops. This looks like this with a VP of 5 and -5. So this is our input. So we want to consider our output. And from our previous notes, we see that the output is not going to be shunt. So it's going to, the negative part is going to come through. Okay. And we're curious about what's going to happen in the positive part, right? So this is going to be negative. A certain VO. So let's go ahead and analyze the circuit. So in the positive region, our current is going to flow like this, and it's going to see a forward bias. And since it's a silicon diode, this is going to be plus 0.7. So essentially, the voltage from A to B is equals to the voltage here from A to B as well, which gives us 4.7, or this is just 4 plus 0.7, or 4.7 volts. So it comes up and it gets clipped right here. Okay. And the same thing happens at this end. So we can go ahead and get rid of our question marks because we know what's going on. And so we can also then consider what happens when I push my current in this direction. When I push my current in this direction, this diode acts like a reverse bias. So it's open circuit. So my current is going to want to flow through this resistor. And again, this becomes a voltage divider circuit where this is V out is equals to -5. Again, because my voltage, it's seeing the voltage at this point as a -5, right, from here, times 5K over, I'm just going to add the 5s. So this is plus over 10K. So then this becomes minus 2.5 volts. So my VO here is minus 2.5 volts. So again, this is clipped between, this shrinks down between -2.5 and 4.7 volts. A couple of applications you can use this for, just as a reference. You can use this for many applications, but a couple of them is voltage protection. For example, if you have an input of 5 volts and you can't help that input, for example, the voltage coming from your wall on your house is a given voltage, but if you had an application where you only needed a certain range, let's just say 4.7 to 2.5, you could use this type of circuit. We can also use this circuit for changing a square wave to a timing of clock signal. So square wave to a clock signal or timing signal. And again, this is shown right here in this example. We went from a square wave to kind of like a clock circuit. Lastly, if we notice that there's a certain part of our waveform that generates a lot of noise, we can use this for some type of signal conditioning, right? So if we notice that there's a lot of noise once we get to a certain 4.7, we can use this signal to cut out that noise and clip that noise, so we get a little bit less of a noisy signal. So these are just a few applications you can use this for. Again, please, if you like the video, like, comment on the video, and also share my videos and subscribe to my channel. Thank you. Have a wonderful day.